Hey everybody, I thought I'd make you a little video that would hopefully review the major concepts behind the majority of the stoichiometry that we did last year. Since most of you are coming from different backgrounds and you've had different teachers who have different styles, I'm not exactly sure of everything that you were covering, so I thought a nice, equal, fair place to start would be let's just review in general stoichiometry. So just to kind of remember, stoichiometry is the process of using a balanced chemical equation in order to kind of relate the amounts of materials to one another. So whether it's trying to say, okay, I have 10 grams of reactant, how much product can I make? Or I would like to make 15 grams of product, how much reactant do I need to add into my reaction? That's the process of stoichiometry. Really great context clues end up being when the question starts talking about one chemical, but then quickly asks something different about another one. That should trigger the idea that, hey, this is going to be a stoichiometry problem. Now, somewhere inside of stoichiometry, regardless of where you came from, I know that you learned about limiting reactant style problems, and you're going to need to be well versed in how to do these. I chose not to include an example problem. There are a ton of them out there on the internet. If you would want another example problem at any time on anything, let me know. I'll make you another podcast and just slap it up onto Edmodo. But basically, limiting reactant problems, the only thing that makes them different is that they'll give you multiple numbers for your reactants, and you have to determine which reactant will limit the amount of product that can be produced. In other words, it runs out first, and then the reaction stops. So it's usually two stoichiometry problems versus just one, and then the correct answer is the smaller answer. So what the heck is this mole thing? Why is it so important? Well, it's a pretty standard measurement that we use in chem, and when we go to set up a chemical reaction, we measure everything out in grams because it's convenient to us, but that's not necessarily how the chemistry actually happens at the core. Chemistry really happens one molecule at a time. So you'll get a certain number of molecules that will collide in space, and then we'll proceed forward to make a chemical reaction. So when we set up a chemical reaction, we need to make sure that we have the correct ratios of molecules in the same pot at the same time. And we can't count them out one molecule at a time. So we need to scale up what that looks like. So scientists came up with this mole thing. And a mole is simply defined as 6.022 times 10 to the 23 particles of anything. Now that means that a mole of one thing is not going to be neither the same volume nor mass as anything else. So they're very unique numbers here, but the one thing that will be consistent is the number of particles inside of that substance. It's always 6.022 times 10 to the 23rd. So, how do we convert to moles? Well, just to remember, you're going to need to calculate a molar mass. So I showed you a little example down at the bottom of this page where we're calculating the molar mass of C6H5. So you'd need to get the 6 times the molar mass of carbon, which is about 12, and then add that to 5 times the molar mass of hydrogen, which is about 1, and that should give you a total of about 77 grams per mole, and that unit is actually very important, grams per mole. So when you want to be converting between a mass and moles, we use this as the conversion factor. And that calculation is going to look a little bit like this. So it's extremely important for you to know how to convert between grams and moles. Particles, molecules, atoms, all of that stuff is nice. We occasionally see that on the AP exam, so you should be familiar with it. But it's never our central focus. Our central focus is really always going to be to try and get to that mole by hook or by crook, however you can do it. So for my example problem, I just simply said, how many molecules are in 40-gram sample of sodium chloride? Well, because it's a molecule, I quickly calculated its molar mass and found that it was 58.44 grams per mole. I took what I was given in the problem and put it over 1, and notice that the unit will cross out from top to bottom of the next box, and that drives that calculation forward. So stoichiometry in general. Stoichiometry in general now is going to apply that same concept, but throw a chemical reaction into the midst. And in general, all stoichiometry problems have about the same 4 boxes. It's just a matter of what unit is going into what box that makes them different. You always start off with a measurement. That measurement is then converted into moles. You use a mole-to-mole ratio, and then convert away from that moles into some other usable measurement. And depending on what state of matter either your reactant or your product is going to be in, will determine the type of conversion that you're going to be doing. So the one that we usually start teaching about is solids, because they're easy to manipulate and the conversions are all very simple. So if you have a solid, you use the molar mass to convert to moles. You can then apply your mole-to-mole ratio, and then again use the molar mass of your second substance to convert away from moles and back into grams again. I tried to give you the rough setup of what that problem would look like without any numbers in it. There are some additional things that you're going to have to remember when we went through and we learned stuff about solids and solid stoichiometry. There are some auxiliary problems that you're going to want to be refamiliarizing yourself with. You should go back and make sure that you can predict the product of any old chemical reaction. So you should be able to differentiate between a double replacement reaction and a redox reaction. So in other words, it's either between 2 compounds, which would make it double replacement, or anything else, which would make it redox. And then of course the subtypes, which would be precipitation and acid-base, synthesis, decomposition, single replacement, and combustion. You're going to want to make sure that you know how to do a limiting reactant calculation, including calculating the amount of the excess reactant that is present at the end of the whole reaction. So if you need help with that one, I will happily make you another podcast. Percent yield calculations, they're very easy. Remember, it's actual over theoretical times 100, and that the theoretical number is always the answer to your stoichiometry problem. Percent composition, mass of a part divided by mass of the whole thing times 100. And then finally, molecular and empirical formula calculations. Those are the ones where you're given grams of each individual element inside of your compound. You convert it to moles, divide by the smallest, and then the answer is the subscript in your formula. So what about if we had liquids with stoichiometry? Yay, liquids. So liquids are measured a little bit differently. They're not measured in grams, they're measured in liters. And we're going to need a decent conversion factor between moles and liters, and that's called molarity. So we are going to be doing a couple molarity calculations here. This again should be pretty much secondhand because we used quite a bit of these last year, regardless of the level that you were in. So again, you start off with your measurement. So your liters go over 1, and then you use molarity as your way of converting between liters and moles. For those of you who are coming out of academic, you were probably taught that you should plug in your liters and plug in your molarity to try and solve for moles in the molarity equation. And if you feel more confident doing it that way, it's fine. There's no one right way of doing any of these problems. But this is the setup that I would use to try and do a solution stoichiometry type problem. Additional knowledge that you're really going to need when you go through your liquid unit, or when you're kind of reviewing your liquid concepts, you should remember how to make a solution from a solid, and that's just an application of the molarity equation. Usually you're told, I would like 1.5 liters of a 3 molar solution. So you plug that into molarity equals moles divided by liters, and then solve for the moles. And of course you can convert those moles back into grams. You could go get the grams, mix up your solution, everybody's happy. You need to make sure that you also know how to do a dilution. That's the M1V1 equals M2V2 equation. A titration and a subsequent calculation. Everybody did these. It's just basically glorified, a little bit more difficult solution stoichiometry calculations. And then just to be a little bit familiar with pH, we're going to cover this in more detail as we go through the beginning part of our AP course. So don't completely lose it if you're like, oh my gosh, I remember nothing about pH. It's okay. Remember that low numbers are acidic, high numbers are basic, and at that point, you're pretty much okay. Okay, and then finally, of course, gases. So a whole bunch of stuff that we learned about gases. I feel like we learned gases for like 3 or 4 months last year. We're going to kind of dial back exactly what you need to remember to almost just PV equals nRT. If you can do a PV equals nRT problem, you've got the majority of what you need for the gas unit. With one nice exception. For some of you in the academic classes, you may not have learned what we call is a standard molar volume at STP. And it's kind of like a molarity that you can apply for gases at STP conditions, which, by the way, is standard temperature and pressure, and that is 1 atm of pressure and 273 Kelvin. So 1 mole of any gas at STP will occupy 22.4 liters. So I used that 22.4 liters to do the conversion down below. And if you notice, it's the same pattern where you take your measurement over 1, convert to moles, mole-to-mole ratio, and then back to a measurement again. The problem changes slightly if you're not at STP conditions, because the only way of converting to moles of a gas at non-STP conditions is by doing a perv-nert problem. So you plug in your pressure, your volume, your temperature, your R into perv-nert and solve for the moles, the N, and then you can plug that into your stoichiometry problem and continue with the mole-to-mole ratio. Additional concepts that we talked about when we were studying gases, not a focus here on this review assignment, but just things that you should probably keep in the back of your head. The combined gas law, so P1V1 over T1 equals P2V2 over T2. Graham's law, which you do learn about in the honors class, but do not in the academic class. It's a simple concept, and it is simply that the larger the molecule is, the slower it's going to move. That's all Graham's law really states. Dalton's law of partial pressure is extremely important. We'll make sure that we cover that in a little bit more detail and when we come back in from the summer here. And of course, kinetic molecular theory. And we'll again talk about that again a little bit when we come back from break. The final thing that we want to make sure that we knit into stoichiometry is how heat factors into this whole thing. So don't forget that when we're writing chemical equations, we can turn it into a thermochemical equation by simply talking about the heat. So we usually have like a little delta H equals at the end, and delta H means change in enthalpy, and that is in units of joules per mole reaction. A positive delta H means that it's endothermic, it's taking heat in and that reaction is going to feel cold. A negative delta H means that the reaction is exothermic. Heat is traveling out and it feels hot. But we can use this delta H to actually interconvert between joules and moles of anything, really, as long as it's in terms of per mole reaction. And remember that we define per mole reaction as the equation that you write in. So your mole-to-mole ratio is really strange, and notice how that looks on the screen here. On the top it says 1 mole reaction on the top over whatever the number of moles is of that original chemical in your chemical equation. So say in your equation you had 5 moles of CO2. Then a 5 goes on the bottom, but it's always 1 mole reaction on the top because that's what was present in your equation that was balanced. So that's basically how you could go between mass and joules. Additional things that you should probably just keep in the back of your mind as we get out of the heat stuff is that we did a whole bunch of calorimetry problems. So there's MCAT equals MCAT calculations, delta J equals MCAT, and we'll be refocusing on those pretty soon. Heating and cooling curves, that's that thing that looks like steps when we used a combination of delta J equals MCAT and delta J equals MC when there was no delta T at the phase change. Phase diagrams, those are those weird pictures that have like a triangular shape on the inside of it that separates solid, liquid, and gases. Potential energy diagrams, 2 weird plateaus with a weird hump in between. We'll take a look at those again when we get back into school. Thermochemical equations, we just talked about those, and Hess's law. And for those of you coming from academic, that's probably a little bit more of a foreign concept. It's going to be a pretty major focus when we hit our thermochemistry unit.